Here's something most people never stop to think about. You're made of atoms, your hands, your eyes, the screen you're reading this on, everything around you, solid, real, touchable. But if you could shrink down, small enough to see what's actually inside one of those atoms, you'd find something that makes no sense at all. Think about everything you've ever touched. A table, a wall, your own hand. It all feels solid, real, permanent. And somewhere in school, someone probably told you why. They said everything is made of atoms, tiny particles, too small to see, but there, always there. And they probably showed you a picture. A little ball in the center, that's the nucleus, and then smaller balls circling around it. Those are electrons, spinning, orbiting, like planets around the sun. It's a clean picture. It makes sense. It feels right. For decades, this is what scientists believe too. The atom was a miniature solar system. The nucleus was the sun. The electrons were the planets. Gravity held the solar system together. Electric force held the atom together. Different scale, same idea. Simple, elegant, beautiful. But then someone did the math, and the math said something terrible. See, electrons aren't just particles, they're charged particles. And charged particles behave in a specific way when they accelerate. When they change direction, when they move in circles, they radiate. They give off energy, as light, as electromagnetic waves. It's not a guess, it's what happens. We can measure it. We can see it. Anytime a charged particle moves in a curve, it loses energy. And an electron orbiting a nucleus is moving in a curve, constantly. So it should be radiating energy all the time, which means it should be slowing down. And if it's slowing down, it's falling. Spiraling inward toward the nucleus, faster and faster. The math was clear, brutally clear. Every atom in the universe should collapse. In less than a trillionth of a second, the electron should crash into the nucleus. The atom should destroy itself. Everything should fall apart. Your body, the ground, the air, all of it should have collapsed the instant it formed, but it didn't. You're still here. The walls are still standing. Atoms are stable. Perfectly stable. They've been stable for billions of years. So something is wrong. Either the laws of physics are broken, or the picture is. Scientists in the early 1900s stared at this problem. They couldn't ignore it. The contradiction was too big, too obvious. Atoms exist. That's a fact. But according to everything we know about electricity and motion, atoms shouldn't exist. It was like discovering that the ground beneath your feet, according to all logic and mathematics, shouldn't be able to hold you up. But it does. Some tried to patch the model. Maybe electrons don't radiate when they orbit. Maybe there's a special rule, a special case. But that felt like cheating. Like saying, the rules don't apply here without understanding why. Others started to suspect something deeper. Maybe the problem wasn't with the physics. Maybe the problem was with the picture itself. Maybe electrons aren't little balls orbiting a nucleus. Maybe they're not orbiting at all. Maybe the whole solar system analogy, the one that felt so intuitive, so obvious, was completely wrong from the start. And that's when things got strange. Because if the electron isn't a particle moving in a circle, then what is it? Where is it? What is it doing in there? These questions sound simple, but the answers, the real answers, turned out to be unlike anything anyone had imagined. The atom wasn't a smaller version of the world we know. It was something else entirely, and to understand it, we'd have to stop thinking about particles and paths and orbits. We'd have to think about something we'd never seen before, something that still, to this day, doesn't fit comfortably into words. There's a moment in science when everything stops. Not because you found the answer, but because you realized you've been asking the wrong question. Scientists had spent years trying to fix the atom problem. They knew electrons couldn't be orbiting the nucleus. The math proved it. The physics proved it. But they kept trying to make orbits work anyway. Maybe the electron orbits differently. Maybe it loses energy slower than we think. Maybe there's a force we don't know about yet. Patch after patch, excuse after excuse. But nothing fit. And then several people actually, at around the same time, stopped and asked a different question. Not, why doesn't the electron fall? But what if the electron isn't the kind of thing that falls? It sounds like a small shift. It's not. It's everything. Think about it this way. Imagine you're trying to understand why a shadow doesn't get wet when it rains. You could spend years studying shadows, measuring them, analyzing them, trying to figure out what makes them waterproof. You could propose theories. Maybe shadows have an invisible coating, but you'd be asking the wrong question. Because shadows aren't objects, they're absences, they're patterns of light and dark. The question itself doesn't make sense once you understand what a shadow is. Scientists were in the same position. They kept asking, where is the electron? But that assumed the electron was a thing, a tiny ball, a particle. And as long as you assume that, you'll never understand what's happening. So they stopped assuming. They asked, what if we're wrong about what an electron is? Not its charge, but what kind of entity it is. What if an electron doesn't have a position until you look? What if asking where is it right now is like asking what color is the number 7? A question that sounds reasonable, but isn't. This wasn't easy to accept. It went against common sense. We live in a world of objects. Things are here or there. You can point at something and say, that's where it is. But inside an atom, maybe that's not how it works. Maybe the electron doesn't have a location. Maybe it's not traveling along a path. Maybe it doesn't exist the way marbles and planets exist. And once you allow that possibility, the entire problem changes. You're not explaining why it doesn't fall. You're trying to understand what it even means for something to be there. This shift took decades. It required letting go of certainty, admitting that the human brain might not be equipped to visualize this. Built to track predators and throw rocks, and we might not be equipped for the atomic scale. We can describe it, we can use it to build computers and lasers and medical devices, but picturing it the way you picture a ball rolling down a hill, that might not be possible. And maybe that's okay. Maybe the question was never, what does the atom look like? Maybe the question was always, what is the atom really? And that question still doesn't have an answer we can hold in our hands. Close your eyes. Now answer this. Where is your phone right now? You know the answer. It's on the table, or in your pocket, or on the desk next to you. It has a location, a specific place. Even when you're not looking at it. That's how the world works. Things exist in places, whether you're watching them or not. A car in a driveway, a star in a galaxy far away, all of them. Somewhere. Always somewhere. Now imagine something different. Imagine an object that isn't anywhere until you look. Not because it's hiding, but because where isn't a property it has until the moment you check. That's an electron. And it sounds impossible, like word games, like philosophy, but it's not. This is what the experiments show. When scientists try to locate an electron around an atom, they can't pin it down. Not because their instruments aren't good enough, but because the electron genuinely doesn't have a single location. It's spread out, smeared, distributed across space. The electron exists as a cloud of probability. Every point in space around the nucleus has a number attached to it. A chance. Maybe there's a 30% chance here, 5% there. And all of those possibilities exist at the same time, in reality, until you measure it, and then the moment you look, the cloud collapses. The electron snaps into one place. You forced it to choose. Before you looked, it wasn't secretly in one place, it was actually in multiple places at once. Think about that. The electron doesn't have a hidden location. It has no location at all, not until observation creates one. Picture a guitar string. You pluck it, it vibrates. Now here's a question. Where is the vibration? You can't point to one spot. The vibration is the whole string, moving, oscillating, creating a pattern. The string is the wave. The wave is the string. What if an electron is like that? A vibration in space itself. This is the idea that changed everything. Scientists started treating electrons not as objects, but as waves. Think of a guitar string. When you pluck it, it vibrates in specific ways, specific frequencies, because only certain vibrations can fit. The wave has to connect at both ends. It has to complete itself. An electron around an atom is exactly the same. It's a trapped wave, and because only certain wave patterns fit, only certain shapes work. We call these shapes orbitals. The difference is everything. An orbit is a path, a route. An orbital is a region, a zone where the electron wave exists. The electron isn't moving around the nucleus. It's vibrating in place. This is why atoms don't collapse. It's held up by geometry. This explains the entire periodic table. Chemistry itself comes from the stable shapes of these electron waves. But remember, it's a wave in probability, and that doesn't look like anything at all. Imagine you're standing at the bottom of a staircase. You want to go up. You can step on the first stair, the second, the third. But you can't stand halfway between stairs. You're either on one step or another. No in between. That's not how we usually think about energy. When you roll a ball up a hill, it can stop anywhere, any height, any position. Energy in our world feels smooth, continuous, like a ramp. But inside an atom, energy is a staircase, not a ramp. An electron can have this much energy, or that much energy, but nothing in between. It's either on step 1 or step 2, never 1.5. This is called quantization, and it's the reason atoms exist at all. Remember the problem. The electron should be radiating energy, spiraling inward, collapsing into the nucleus. But it can't, because there's nowhere to collapse to. The electron is already on the lowest step, the ground state, the bottom stair, and there is no step below that. It's not that the electron doesn't have enough energy to fall, it's that falling isn't an option. The staircase doesn't go any lower. So the electron stays stable, not because it's motionless, not because some force is holding it up, but because the universe only allows certain energy levels, and the electron is already at the lowest one permitted. This is why atoms emit specific colors. Why neon glows red. Each jump, each drop from one step to another, releases a specific amount of energy as light. Red light, blue light, green light. Each one corresponds to a specific jump, a specific staircase. And every element has its own staircase, its own set of steps. That's its signature, its fingerprint. The electron is the same. It exists as a wave, a pattern, and that pattern has a minimum energy, a lowest configuration. You can't have less than the minimum, so the atom doesn't collapse. You now know the electron isn't a tiny ball, it's a wave, a cloud, a pattern of probability. It exists in many places at once. Until you look, it all works, but no one can tell you what it actually is. Richard Feynman spent his life working with quantum mechanics, and even he admitted nobody truly understands it. The why remains unanswered. Maybe it always will. Maybe we've reached the limit, not of science, but of intuition. The universe doesn't owe us an image, it doesn't owe us comfort, it just is, and sometimes that has to be enough.